Okay, so we're going to do part C to 2004 E1. It's a cylinder problem. So we have a non-conducting um, shell with uniform density rho surrounding another cylinder with uniform charge density lambda. So that's charge per length located at the center. We want to use Gauss's law, find the electric field in those three regions: R less than R1, so that would be in that white area; R less than R greater than or equal to R1 but less than or equal to R2, and then R greater than R2. That's where we want to find the electric field. Okay, so let's do part I first, and we need to first of all remember it's a cylinder, so that cross section picture might be confusing. You might think it's a sphere, but it's a cylinder. Okay, and so we need to pick a Gaussian cylinder that is in that white region. Okay, so if I do that, I'll use this picture right here to draw it. Okay, so our Gaussian cylinder is going to be this thing. Okay, they tell us that these are infinitely long, so that we're just looking at a piece of it, by the way. So we need to have defined dimensions for our Gaussian surface. Okay, so there's our cylinder. I'll draw it on this picture also. It's going to have radius of little r. Okay, has length of L. Okay, so for part I, we're going to use closed integral E dot dA equals Q enclosed over epsilon naught. Okay. The left side of the equation, notice that the electric field only goes through the wall of the cylinder. The sides don't matter. So this is technically three integrals: three of one side, E dot dA, plus integral of another side, E dot dA, plus integral of the wall of the cylinder, E dot dA. But the sides actually don't matter. These are zero, because the electric field is parallel to the sides, but it goes right through the wall of the cylinder. So we're going to be left with E times the area of the wall of our Gaussian cylinder. Gaussian cylinder. Okay, that's a G, by the way. That's it for the left side. I guess we could write down what the area is. The area would be E pi little r squared. Okay, the right side of the equation, we want to figure out how much charge is enclosed. It encloses a piece of that inside cylinder lambda, right? So it would contain just this part. That's kind of too bold. Let's do that. So it contains this little piece right there, lambda, that length of it. Okay. So then, Q enclosed equals lambda L, right? Because lambda is charge per length. So Q enclosed equals lambda L. So then we have I messed up on the area of the wall of the cylinder. It's not pi r squared. That would be the sides. Let me start that over, sorry. It would be L times the circumference, so L times 2 pi little r. Sorry about the confusion. So we're going to get, setting the left side equal to the right side, we're going to have E 2 pi r L equals lambda L over epsilon naught. So E equals, if I divide both sides by 2 pi RL, the L's cancel, and we're left with lambda over 2 pi r epsilon naught. So that's the electric field in that region. Okay, so part 2, We want to know the electric field when R1 is or when R is in between R1 and R2. So in this region right here. So we're going to draw a new Gaussian cylinder. It has a new radius, but still the same length. So new radius is R. Okay. The left side of the equation will look exactly the same. We're going to get closed integral E dot dA equals Q enclosed over epsilon naught. And this left side looks exactly the same. E 2 pi RL. Okay, so we just need to deal with Q enclosed. Okay, how much charge is enclosed? So the amount of charge enclosed is going to be the lambda part, which we already found is lambda L, but it's also going to contain this charge. So we got to consider that also. Okay. So to write that out, we're going to have E 2 pi RL. Okay, so Q enclosed is going to equal the lambda L plus that sum of that volume density charge. So we'll have rho, which they give us, times some volume. Okay, what volume do I want? I just want the volume that's shaded purple right there. Okay, so I guess we'll call that volume of the, I don't know, just leave it as volume. Okay, so what volume is that? It looks like it would be the volume of a cylinder with radius R, minus the volume of a cylinder of radius R1, right? Because we don't want to count the white space or lambda. So that volume is going to equal the volume of a cylinder of radius R1, no, not R1, sorry, just R, minus the volume of a cylinder of radius R1, which is equal to volume of a cylinder is the length times pi R squared. So, and then minus L pi R1 squared. Okay, which is just equal to L pi R squared minus R1 squared. Okay, so plugging that in, we have lambda L plus, we have pi R, just copy it, L pi R squared minus R1 squared. Okay, so we could factor out, what could we factor out? We could factor out L and just have lambda plus pi R squared minus R1 squared. And now we can set the left and the right side equal. So we have an E times a 2 pi RL equals L lambda plus pi R squared minus R1 squared. Divide that stuff by epsilon naught. Dividing both sides by 2 pi RL, the L's cancel, and we're left with E equals, we have a lambda plus pi R squared minus R1 squared, divide by 2 pi R epsilon naught. So that is for that region. And then last one, when R2 is greater than when R is greater than R2. Okay, so now when we do that, now our Gaussian cylinder is going to be outside of everything. So here's our new Gaussian cylinder. It's outside of everything, has radius of R. Okay, so on this picture, it's out here. Doesn't look like a circle, but it is. So now when we consider how much charge we want, we are going to be taking all of this shaded region this time. Okay, so our volume of that shaded region is going to kind of look like the original equation that we had. going to kind of look like that, except for we're going to replace R with R2. Okay. So what part is this? Part 3? Part 3. So we're going to have the left, so you don't want to spend a whole lot of time. You don't want to go through everything again. The left side of the equation, we get E 2 pi R L. Okay, the right side, Q enclosed, again, it's going to be lambda L plus rho times the volume. And that volume is going to look exactly the same. Okay, so we had, what did we have? We had, you know what? I forgot my rho. Gosh, this is bad. I forgot my rho up here. Right, I just had the volume. So rho is attached to all of these. So rho times that volume, it's going to be L pi, rho L pi times, instead of R squared, we're going to have R2 squared minus R1 squared. And that should be it. So that's what that will look like. And then setting the left side equal to the right side, we have E 2 pi RL equals, factoring out an L again, we would have an L lambda plus rho pi R2 squared minus R1 squared, divide by epsilon naught. I'm going to divide both sides by 2 pi RL, and the L's cancel out again. So we get E is equal to lambda plus rho pi R2 squared minus R1 squared, divide by 2 pi R epsilon naught. And that's the electric field outside.